Our next speaker is Ravi Singh from Juniper, where he is the principal software engineer. He'll be talking about running MPLS efficiently in ring networks.
Good afternoon. Running MPLS efficiently in ring networks. Why are we even talking about this? As probably most of us know, there are plenty of rings out there, typically in the access and aggregation. The most common example being that to connect multiple cell sites. Now, the question is, how widely is MPLS deployed in such rings? And the very fact that I'm talking about it here, the answer is not very much. So this presentation is essentially going to be in 3 parts. The first part is going to be a quick recap of what are the network realities and how MPLS solves those enables those realities, and what are the properties of the ring, and why is it so that rings and MPLS haven't sort of played along too well so far. And in the third part, we'll talk about resilient MPLS rings, which is an architecture by which some of the reasons why MPLS is not so prevalent in rings, those reasons are alleviated. And it's my belief that with RMR, MPLS and rings can go together, and many of the pet peeves that prevent MPLS from being widely deployed in rings can be addressed. So with that said, let's quickly jump in and see what are the network realities. If you're an operator, you care for uptime, you want your traffic to go through, and you're running a large network, and you invested the resources to put that network there. So you want to make sure that the network's being well utilized. You don't want there being routers or links that are just sitting there underutilized. I mean, that's, doesn't make good business sense. And also, sort of alluding to the same point, when setting up a network, operators care a lot about the price points for the equipment that they're putting in, routers as well as links. And not just that, also what it would take to keep the network running in the long term. And so how has MPLS enabled that? So MPLS enables uptime by having fast reroute. So basically gives you typically under 50 milliseconds of restoration for your traffic. So it enables uptime. Now, in regards to enabling effective network utilization, MPLS enables that as well. By using RFCP-TE LSPs, you're able to traffic engineer paths through your network, paths that may not be the shortest paths, but yet maybe the underutilized paths over which you carry traffic. As a result, utilizing your network better. And our MPLS also enables ECMP load balancing over ECMP/lag by using techniques like entropy label, which in the core enable hashing, which enable load balancing, or rather, which enable hashing to facilitate load balancing by hashing just on the entropy label rather than have to hash on the innermost headers. And in addition, MPLS enables carving out paths with specific bandwidth constraints through your network. And also, not just that, the LSPs that are set up in your network, you can resize them by using features like auto bandwidth, which sort of react to how much traffic is actually going over the LSP, and in keeping with that, readjusting the amount of bandwidth that's allocated for that LSP through your network. And in regards to financial efficiency, if you're running a large core network, by running an MPLS core, and by deploying various services like layer 3 services, layer 3 VPN or VPLS or EVPN over the shared MPLS core, by utilizing the single network there, I mean, there is financial efficiency to be had. So now let's look at rings. What are the properties of a ring? Thereafter, we'll look at why, what is it about rings and MPLS that makes them so far not play along that well. So a ring is a simple topology which gives complete connectivity for n nodes with just the adequate number of links between those nodes. So that comes at a cost. The cost is that you just have 2 paths between any 2 nodes. And if there were to be one failure somewhere in the ring, you just have one path between any two nodes. So that is distinct from a regular, a very meshy core network where you'd have multitude of paths between any two nodes. So basically, having just two paths between any two nodes leads to there being significant path overlap in traffic between any pair of nodes. So for example, in this picture, for the traffic going from N7 to N1, the path for that, and the path for N5 to 2, N5 to N2 has the overlap as shown by the red line. And so where is this acceptable, that you have such few paths between nodes, and as a result, such proneness to there being multiple failures, making your network partitioned? That's acceptable only, where the stakes are probably lower, which is in the access and aggregation, and that's where the rings are most prevalent. So we've talked about what do operators care for, what MPLS enables, what are the properties of a ring. Now let's look at the properties of RSCP-TE LSPs and LDP-enabled LSPs and use that to sort of tie it into why operators may be hesitant to enable MPLS in rings. So in this network diagram here, and by the way, this is not a ring, so this is a simple representation of a typical core network where you would have routers R1 to R4 be the provider edge routers hosting some service like L3 VPN or MPLS or whatever. Now, to get complete connectivity between these routers using RSCP, you would have to set up a full mesh of LSPs. So the demonstrated in this picture are those three lines, the colored lines coming from R1 to each of the other three edge routers, the provider edge routers, R2, 3, and 4, showing the three LSPs going from R1 to each of the other PE routers. And likewise, from each of those other routers, the three LSPs going to the other three routers. So in essence, you have order of n square RSCP LSPs. So that's typically, operators don't like that. And we look at the next slide how this gets even worse on rings. Now, in this network, there is, if you notice, there's sufficient path diversity to get from any provider edge router to another. There are multiple paths. And if there were to be failure on some link, which happens to be on the path of an LSP, it'll be a two-step process to repair that. Firstly, local repair would kick in, assuming you have a protection path for that link or node going down, and the RSCP LSP would get signal over your bypass LSP, and eventually global repair will kick in, wherein the ingress router for the LSP would resignal the LSP on a brand new path. And so the key thing is, while your local repair is carrying your traffic, your LSP may not be carrying may not be taking the most efficient path, and there is signaling churn due to global repair. And as you see in this network, because the aim is to exploit path diversity as much as possible, there isn't really a multi-point to point RSCP LSP that exists in the standards today, prior to talking about RMR. And this becomes sort of problematic on rings for the reasons being the properties of the ring that we talked about, and we'll talk about it again in a subsequent slide. Now, if you were to be running LDP to set up your LSPs in a network, so LDP doesn't give you any traffic engineering using constraints. It does not allow bandwidth accounting or setting up LSPs with specific bandwidth constraints in the network. And it does give you some failure protection if you use a technique like LFA, loop pre-alternates, or remote LFA. However, LFA and RLFA do not give complete protection against all failures in many topologies, and ring being one of those. And even to compute the protection paths using RLFA, there's sufficient, there's a reasonable amount of churn, which by design itself can lead to microloops. So those were sort of the advantages/disadvantages of using RSCP or LDP as a signaling mechanism for MPLS LSPs in general. Now let's look at how those become sort of relevant when talking about rings. So rings are a strange topology that, like we talked about. There's only two paths between any two nodes. And by running RSVP in a ring to get your complete connectivity between n nodes, you're setting up order of n square LSPs when they're actually sharing, when they're actually overlapping in their paths quite a bit. So what does that really give you? All it causes is excessive state, excessive RSVP state in your devices in the ring. And as you all know, the devices in a ring typically are not the higher end devices. They are sort of smaller boxes and more cost optimized. So having order n square LSP state is sort of detrimental to running a network and running it well. And also, if you were to have a failure in your ring, for example, as demonstrated in this picture, if the link between N3 and N4 were to fail, then the green LSP, starting from N7 going to N1, would get rerouted at the point of local repair, which being the node N4. The traffic would go back, come up to N7, and then go all the way up to N3, that being the merge point, and then it takes the what would have been the original path for the LSP to go up to N1. So essentially, there is double usage of bandwidth between the point of local repair and the ingress of the LSP, and again between the merge point and the egress of the LSP. So this is not very efficient. And so if MPLS and rings were to play together, this would be one of those prime things, along with reduction of state on the devices, that would make that's a prime candidate for the picking when making things more efficient. And in a subsequent slide, we'll look at how that is accomplished. So in essence, what we are really saying is the properties of a ring make general purpose MPLS not very suitable for running in the rings. And that's probably the reason why MPLS and rings, they haven't gone together very much so far. So basically what we need is, we need to be able to set up the optimal number of LSPs in the ring so that local protection is utilized efficiently and the ring bandwidth is utilized efficiently. See, the key thing is what I mentioned before, that because of the path overlap here between any LSP going between pairs of nodes in the device, in the network, the path overlap itself causes bandwidth in a ring network to be scarce, because if one ingress is asking for more bandwidth for its LSP, it's coming at the cost of other potential LSPs in the network. And the reason for that being the significant path overlap. So that's again another problem that can be improved upon, and that's one of the aspects that RMR helps with. And so let's talk about what is RMR, resilient MPLS rings. So what does it really give us? It gives us a way for the rings to become self-configuring. The nodes in a ring discover themselves as being part of a ring without there being too much explicit configuration. And with RMR, it makes provisioning for RSVP LSPs in the ring much easier compared to provisioning RSVP LSPs that exist today. So today, the order of n square LSPs that we talked about, each of those has to be individually configured. With RMR, that need to individually configure LSPs goes away. In fact, you do not configure any LSP anymore. All you configure in regards to the ring is the nodes belong to a ring, and you don't configure that on all the nodes, and you configure nothing in regards to LSPs. The LSPs set themselves up, and we'll look at in a subsequent slide how. So by having fewer number of RSVP LSPs in your ring, you're also reducing the amount of control state that will exist on each of those nodes. That will enable the fibs to be smaller, and that potentially allows for cost-optimized hardware to be used. And that plays to the financial efficiency thing that I mentioned on the first slide that operators care greatly about. Now, if you were to be using LDP on your ring, so by using RMR, you get more effective failure protection as compared to other schemes that exist out there. And we look at in a subsequent slide, how it's more effective. So basically, what is an RMR LSP? What are its characteristics? So in this ring of 10 nodes, N1 to N10, there will be N ring LSPs that will signal themselves once the ring is auto-discovered and the self-configuration process has finished. So each ring LSP will be a multi-point to point LSP. So by virtue of that, it means it has one egress router. And demonstrated in this picture, by virtue of those colored lines, are 5 ring LSPs, where the node where the 2 arrows meet for a given colored line, that happens to be the egress for that ring LSP. So let's consider the ring LSP, the green ring LSP, which has the node N1 as the egress. So since this LSP is a multi-point to point LSP, what that means is any of the other 9 nodes can send traffic to N1 by putting it on this green ring LSP. So what does that mean? So let's look at it, describing what it means from a point of view of nodes N3 and N4. So N4 has each of these nodes has some traffic shown as ingressing at that node. Now, the traffic ingressing at N1 is irrelevant for the purpose of talking about ring LSP1 because N1 is an egress for that LSP. So we can ignore that traffic. That's not relevant for ring LSP1. It may be relevant for other ring LSPs. So now, talking about nodes N3 and N4 as representatives to illustrate the point of how this MP2P LSP will work. So traffic that ingresses at N4 intended to go to N1, that'll have a label pushed on it for, okay, actually before that. So the ring LSP is made of 2 sub-LSPs, one going in the clockwise direction, the other going in the anti-clockwise direction. So now talking about N3 and N4, if N4 were to send traffic on the sub-LSP going in the anti-clockwise direction, it would push the label that N3 advertised to N4. And at N3, that label would get swapped for what N2 gave to N3. But the key thing is the traffic that ingresses intended for N1, that ingresses at N3, will end up pushing the same label, that is the label advertised by N2, as the label that is getting swapped for the traffic coming from N4 going via N3 to N2. So in essence, there's only state for sort of 2 end state. So compared to using regular RCPTE, instead of having n square state, order of n square state, now there's state for order of n. So in summary again, each ring LSP is multi-point to point. It's made up of 2 sub-LSPs, one going in the anti-clockwise direction, the other going in the clockwise direction. And any node can put traffic on a sub-LSP of a given ring LSP, and it may in fact use both the sub-LSPs of the ring LSP, but the key thing is that since you don't want to cause reordering, traffic for a given flow must always take the same sub-LSP. When I say always, I mean prior to a failure. So since we have a ring LSP, which may carry traffic from multiple ingresses, and different ingresses may have different bandwidth requirements in terms of how much traffic they wish to send to the egress, what this means is that the ring LSP will have associated with each of its hop for the LSP a different bandwidth reservation. So basically, for the traffic going from, for the green ring LSP, from N5 to N4, there may be 1 meg reservation. If N4 wants more bandwidth reservation for traffic going to N1, that would be additive. So how would protection work? So protection conceptually is very simple. When you have one failure happen somewhere south of a node, that node essentially switches the traffic from the ingress, from the sub-LSP that's bringing traffic in to the sub-LSP that's, to the other sub-LSP. And there are no bypasses or detours that are used. So we'll talk about the protection aspect again on a subsequent slide, but let's quickly run through how would you provision this. So I mentioned earlier that you don't configure LSPs individually. All you configure are ring IDs. So on the interfaces of the device that belong, you know what interface corresponds to your fiber, and on that interface you configure the ring ID, and you don't have to configure it on every node in the network. You configure it on a subset of the devices, and by virtue of signaling, the other nodes in your network learn what the device on the other end thinks his ring ID is. And such a node, which doesn't have a ring ID configured on that interface, let's call it being in promiscuous mode on that link, and it acquires the ring ID that it hears, and it configures itself as being part of that ring. So in summary, we don't configure individual LSPs, we configure ring IDs, and the configuration for ring IDs, since it's tied to an interface, it'll work over a number of interfaces as well. So let's look at this picture. So to the right is sort of a core network attached to which are 3 rings, and to the left is a blow-up of ring Y. So on ring Y, there are 4 interfaces, I1, 2, 3, and 4. Interface 3 is attached to R4. And on interface 1 and 4, we would say these interfaces belong to the ring. On one of these interfaces, shown in picture being I1, we could say this belongs to ring interface, ring ID Y. And by virtue of having this configuration, via the IGP, the nodes will discover themselves that all of us belong to this ring. And once the ring discovery is complete, the LSP signaling shall start. So we've already talked about the first 2 bullets. So as once you have a ring that's already up there, nodes and links may come and go, and the ring discovery process and rediscovery process will have self-healing properties, in the sense that as part of discovering the ring, the nodes try to agree upon what's the largest possible ring that they together constitute, and once there's agreement what the shape of the ring looks like, as in what the constituent nodes of the ring are, that's when the LSP signaling shall start. So if I had to summarize this in three phases, the first step would be each node that knows what its ring ID is, it starts sort of advertising through the IGP what its ring ID is, and the nodes in promiscuous mode acquire that ring ID and pass it on. And eventually, a node gets designated, being called the master node, which sort of determines when is it that it is agreed upon that the ring is completely discovered. And that would be when each node has sort of indicated, I know my anti-clockwise and my clockwise neighbors, and once the master realizes it too has had a message loop around to it saying that, indicating that everybody on the path agrees what the clockwise and anti-clockwise neighbors are, that's when the ring discovery completes. Okay, so what does a ring look like in steady state? So we've already talked about this, so I'm going to sort of rush through this. So there are 2 sub-LSPs, and you may send traffic at any ingress in either direction, but for a given flow, only on one sub-LSP. Now let's see what happens during a failure. So let's say that the link between N3 and N4 fails. At that time, N3 will switch traffic from the clockwise sub-LSP to the anti-clockwise sub-LSP, and N4 will switch traffic from the anti-clockwise sub-LSP to the clockwise sub-LSP. That's the model equivalent of local repair in ring under the RMR framework. And in regards to global repair, there is no resignaling of the entire ring LSP. Rather, what happens really is that after the local repair has kicked in, progressively, each node on the sub-LSP, on a given sub-LSP, as you sort of walk away from the point of failure, each node correspondingly starts to switch traffic to the other sub-LSP, so that your traffic isn't going all the way up to the point of failure and sort of looping back. And that's the model equivalent of global repair. And let's just move on. So the key thing about how bandwidth is managed in RMR is that since you may potentially send traffic on both the sub-LSPs, you're able to utilize your ring better. And by being able to use both the sub-LSPs, there's potential for reducing preemptions. Okay, so how does this compare to regular RMR? So as far as RCP TLSPs are concerned, there's much less provisioning overhead. You just configure ring IDs. There's no individual LSP configuration. So that's quite a bit. If your rings are, of a certain size, that makes a huge difference. And also, because of the way the signaling for RMR LSPs work, the amount of state on the nodes is reduced from order n square to order n. And there is no resignaling of the LSP as part of global repair. There's only resignaling if you wish to adjust the bandwidth, the per hop bandwidth of a given LSP. And since, there are only two parts in a ring, so there's really no recomputation. So the concept of EROs is just, it exists nominally, but doesn't play that great a role. And in regards to LDP signaled RMR LSPs, there is complete ring protection by design because you're setting up both those sub-LSPs. So essentially, both the sub-LSPs may carry traffic at the same time. And because of that, since they're both already usable, there's no potential for micro loops. And let's move on. So what does RMR enable? And what protocol extensions will it require? And so this is based on a draft in the IETF, which sort of defines the architecture for RMR, but there's more work to be done in terms of defining extensions for the IGPs and for RCP and LDP to make the signaling, the auto discovery and the signaling of the LSPs sort of be more crisply defined. That's a work in progress. And in terms of features enabled, so the key thing that I think all of you care for is the use of lags in the network. So whereas earlier you would have to configure a lag NAE bundle explicitly, in this case, by virtue of the auto discovery of the ring, the presence of multiple links between a pair of nodes would automatically get accounted for, and the lag would appear to be a single link. And as components of the lag go up and down, it affects the ring discovery considers that, and it'll require much less configuration for configuring lags. And so what we talked about so far is from the point of view of a single ring, but potentially there could be a ring made up of other rings, or there could be nodes and links that are participating in multiple rings. So there is provision for making that happen. We can't just can't, but constraints of time prevent me from talking about it right now, and also it's not defined in the IETF draft yet. It shall be very soon. And in summary, so RMR makes MPLS easier to deploy in rings. It makes configuration much easier, and it enables reduction of control state on nodes in a ring. And by virtue of being able to utilize both the paths that exist between a pair of nodes for forwarding labeled traffic, it is utilizing the bandwidth effectively. And it helps prevent link dual traversal by virtue of the global repair, the cascaded global repair scheme that I described in one of the earlier slides. And here is a pointer to the draft that defines the framework right now, and additional drafts in regards to the IGP and the RCP/LDP signaling shall be forthcoming in the IETF very soon. And with that, I conclude. And any questions, please? Well, looks like there are no questions. Thank you very much.